Hey guys, today we're going to talk about motion with constant or uniform acceleration, which basically means that the acceleration stays the same no matter what. Now then, let's draw a velocity time graph with a constant acceleration. So if the acceleration is constant, you end up getting a linear function, such as, let's say this, which has an initial velocity of v naught and is displayed by the function v of t. Now then, we know based on our knowledge from grade 9 math that v of t, v as a function of t, would be equal to kt plus b, being a play on y equals mx plus b, where k is the slope, t is the x variable, and b is the starting point. And just by looking at this, we know that at v of 0, we get b, which we know is equivalent to v naught. So we can remodel this equation as v of t equals kt plus v naught. Now then, if the velocity as a function of time, or we could just say the velocity is equivalent to kt plus v naught, then if I were to theoretically take the derivative of this function, but end up dv as respected to dt would give me k. If you remember from our last lesson about instantaneous acceleration and average acceleration, dv by dt, which is the change in velocity over the change in time, ends up giving us an acceleration function, especially this specific instance gives us the instantaneous acceleration function. So we can say that k is equivalent to acceleration. This ends up giving us a function called, which is v equals at plus v naught, where the final, whatever velocity we want at a certain time, will be given by the uniform acceleration, that specific time, and v naught, the original velocity. Now, what if we want to look at position, though? Well, knowing that we have this function of v and t with a v naught, which has a equation of v equals v naught plus at, we can specify that the average velocity is equivalent to 1 over 2 times the initial velocity plus whatever velocity we're comparing it to. And if you remember from this formula, that is equivalent to 1 over 2 times v naught plus, and if we plug this in here, v naught plus at, which ends up yielding us 1 over 2 times 2 v naught plus at equals to v naught plus at over 2. However, we also know that the average velocity is equivalent to x minus x naught over t, being the change in position or the displacement over time, which can also lead us to the equation that x minus x naught is equivalent to time times the average velocity. Now, if we plug this into our previous equation, we can end up getting that, if we bring this down, v average equals v naught plus at of 2. You can see v average actually is x minus x naught over t, which is equal to v naught plus at over 2. We're going to try and put this in terms of the final position, because that's what we're trying to find here. So we're going to multiply out the time and add in the final position. So this is how you find the position as a function of time. Now then, if we were to eliminate the variable of time between the two equations, so I'm talking about these two equations, v equals v naught plus at, and x equals x naught plus, x equals x naught plus v naught of t plus at squared over 2. What I would do here is I would say that from this equation here, t equals to v minus v naught over a and plug that into the above equation. Plus a times that squared, which I can take out the denominator, as you'll see in the next step. If I take out the denominator, and it'll move this to the bottom as 2a squared and cancel out the top, leaving us with v minus v naught squared over 2a. If I were to multiply, if I were to move the x naught to the left side and multiply both sides by 2, no, 2a, my bad. Yield me 2v naught times v minus v naught, which will be added to v minus v naught squared. Then we can see that 2v naught will end up canceling out in the two steps. If we expand it, 2v times v naught minus 2v naught squared plus v squared minus v times v naught times 2 plus v naught squared we'll see this cancels out this, and you'll be left with 2a times the change in position, which is actually 2ad, we can call it, is equivalent to v squared minus v naught squared, which is actually one of our big 5 kinematic equations. Now then, let's do a practice problem. Assume I were to have a cat. This cat, or somewhere here, not really the best at drawing, but, and were to fall and a constant rate of g being the acceleration, a distance of 1 meter. And I really wanted to find the final velocity of this cat, right? How will I do so? Well, we could use the formula that I just derived here. So, we know that the initial velocity is 0 because the cat did not propel itself, it simply fell, and as thus, it had no initial driving force. So if we set v0 equal to 0, we will get 2ad equal to v squared based on this formula here and removing the v0. As I said, a is equivalent to some variable g, which is the gravity, and d, we know it as 1. Take the square root of 2g, and that's your final velocity. So yeah, hopefully this was somewhat helpful. I know there was a lot of derivation in this lesson. However, hopefully we're trying to get this all out of the way early so that we don't need to do as much derivation later, and understanding this is very essential for later on when you actually try to solve problems, as it helps your way of thinking about kinematics. Anyways, have a great day.